My name is Diogo Ribeiro. I'm from Portugal, and I'm currently doing my PhD at Université Laval. And my PhD is about element mobility in metasedimentary belts in the Superior Province and its implications for gold systems. And in this project, involves a partnership between 4 different institutions. So Université Laval, where I am at, Laurentian University, KIT in Germany, and Stockholm University. I'm going to start just by a brief introduction to the source of fluid and gold, which is kind of similar to what Adrian just did, and then talk a bit about my project, the objectives, and what I've been doing since this last summer. So different sources have been proposed for sources of gold, such as metallic fluids, magmatic fluids, which may interfere in orogenic gold deposits, but cannot solely explain their characteristics. And there's not a spatial correlation, consistent spatial correlation between these type of deposits and intrusions. So it's generally accepted that the fluids and the gold is sourced by the metamorphism of the surrounding rocks. And in 2010, Phillips and Powell proposed a Divilitization Model, which foresees the liberation of fluid and other components by the breakdown of specific minerals during prograde metamorphism. And they specifically focus the transition between green schist and amphibolite facies, since they have really contrasting mineral assemblages regarding their volatile content. And there is usually a decrease in the moral proportions of hydrous phases like chloride, which releases a substantial amount of fluid. Also diminishing of model pyrite, which tends to break down to pyritite and release sulfur, according to this equation. And if the pyrite is already gold bearing, gold could be released at the same time as sulfur. And so with this model, we would be releasing fluid and gold at the same time, excluding the need for further leaching of gold. Besides that, there is also a decrease in the moral proportion of carbonate minerals, for example, which leads to the increase of CO2 in the fluids. And there are some studies that show that, in fact, the dehydration of metasedimentary rocks leads to the release of significant amounts of CO2. So phase equilibrium modeling predicts that these two reactions, the chloride breakdown and the pyrite breakdown, which are particularly important, that they occur at similar conditions, and they are basically temperature dependent, as you can see by their high slope. And so we have a sulfur window in which the content of sulfur within the fluid increases with temperature and coincides with the chloride out reaction. Works with phase equilibrium modeling in metasedimentary rocks show that besides sulfur, there is a high mobility for gold, arsenic, and antimony. And these predictions have been tested in actual rocks, mostly by Pitcairn, with ultra-low detection limit analysis. And the authors collected samples from different metamorphic zones, so rocks that were metamorphosed at different temperatures, and then compare their gold content. And as you can see, there's a trend, systematic trend for decreasing of the gold contents depending on with increasing temperature at which the rocks were metamorphosed. And in other articles, the same trend is seen for both arsenic and antimony. These articles are in Phanerozoic and Neoproterozoic rocks, but recently Pitcairn and others also published this paper in geology, this time in Archean rocks. In the Pontiac, they collected metasedimentary rocks from Buenoranda and Valdor, and they did ultra-low detection analysis for gold and trace elements on those samples. And the results show that, in fact, again, there is a systematic decrease for gold, arsenic, and antimony with increasing metamorphic grade. So they conclude that gold was in fact mobilized during prograde metamorphism. However, there are some things missing, such as the constraints of PT conditions. As you can see here, the samples are sorted by, not by temperature, but by metamorphic zone. So they don't have temperature for those rocks yet. So that's missing. Also, it's important to keep track of the key metamorphic reactions leading to divilitization, and which is the composition of those fluids. And also, it's important to track the mobility of the elements, the variation we see in a whole rock, and validate that at the microscale with in situ chemical analysis. So this is kind of an introduction to what I'm going to do in my project, which, and its objective, its main purpose, it's to address the role of the metasedimentary belts in the superior province, mainly the Cognac and Quetico subprovinces, as possible sources of fluid ligands such as sulfur and chlorine and metals, especially gold, of course. And what I'm going to do is track the mobility of these elements during prograde metamorphism. And for that, I'm going to use a typical whole rock geochemical analysis and also ultra-low detection limit analysis, which are also whole rock, but for specific elements. And combine that with in situ chemical information from specific metamorphic minerals at different metamorphic conditions, and see the chemical variation of those phases. And this whole information will be complemented by the work of Adrian and Isaac that are doing constraining the PT conditions in the Cognac and the Quetico. So the ultimate goal is to have an optimal PT conditions for the release of gold-bearing fluids, and as they do in petroleum geology for the oil window, this would be kind of a gold window. So the project will be focused on 3 areas: one in the Cognac, which is a Buenoranda, an endowed area, and then 2 in the Quetico, Geraldton, which is moderately endowed, and Thunder Bay, which is considered to be barren. So I went on the field this summer, and I collected, I did a sampling that I tried to have the best spatial coverage as possible. And if we look at Buenoranda, for example, as you can see from this map, the metamorphic grades increases from north to south. And for each metamorphic grade, I tried to have a sampling that had best spatial coverage, the best spatial coverage as possible. So I did the exact same methodology for Thunder Bay and Geraldton. In these areas, the metamorphic grades increase from the periphery towards the center of the belt, but the methodology is exactly the same. So samples from different metamorphic zones, different protoliths in different metamorphic zones, and then compare and see the differences. So after the field, I had these main lithologies, so metasedimentary rocks from gray rock to peelites, and mafic rocks, a total of 270 samples, and information from about 300 outcrops. I classified these samples regarding their alteration in the veins. So how much volume of the rock was affected by the alteration in the veins, and how easy it was to take them out when I was cutting the rock. And also classify them regarding their sulfite content, mainly the distribution of those sulfites, if they are disseminated along foliation or within fractures. So I used this classification to select the samples for ultra-low detection limit analysis, and the main criteria were to avoid any alteration in veins. I was more rigid with the veins because they're the result of hydrothermal circulation. Most of it was post-metamorphic, so that would change the geochemical signature of the rock. And since I want to get the primary signature, I must avoid the veins. And also for sulfides, I would exclude samples that had sulfides within fractures, because I interpreted them as being epigenetic, so post-metamorphic, and those would also alter the primary signal of the rock. So, but in specific cases, I would include some samples that would be discarded at first, in case I was missing some porphyrit variety and spatial representativity from some specific metamorphic zones. And for key outcrops, for example, for outcrops where Adrian or Isaac are doing some modeling, I would include samples that at first could be excluded. So in the end, I selected about 140 samples for ultra low detection limit analysis. And this is their distribution. So as you can see, as a spatial coverage as big as possible for every area, and porphyrit variety. So that's what we want to begin with. So for ultra low detection limit analysis, there is a traditional method developed by Pitcairn, which involves multiple acid digestion and then chromatographic separation of gold, for example, if you're trying to measure gold, and then analyzing by ICP-MS. This has a very low detection limit, from 2 to 20 ppts. However, it is very time consuming, leads to sample dilution when you dissolve it in acid, and it's quite dangerous because you use like 4 different acids. So we're going to try a different approach to do whole rock geochemistry by LAICP-MS in pressed powder pellets. So when after milling a sample, the powder has to be milled again. So this is called nanomilling, to reach such a degree of fineness that we eliminate possibility of nugget effects. So that's the main objective of that. And then the pellets are assembled and analyzed by LAICP-MS. So the detection limit is not as low as the previous one, the previous method, and there may be some interference with tantalum and hafnium oxide, but these can be corrected. And this method is much faster, cheaper, and safer. And if we don't get good analysis with, or if we get analysis below the detection limits with this method, we may resort to this one to see if we can get better results, but only for specific samples. So one more thing, to do this kind of analysis, since we are measuring such low quantities, we need to be extremely careful about contamination. So the samples cannot contact with metal. So I had a problem to start with because I cut the rocks with a metal blade. And for that, because of that, I had to grind the samples. So this is a grinding wheel made out of aluminum oxide grains with a vitrified bond. And I used this to basically remove the surface, all of the surfaces that were in contact with the metal blade. Then the samples have to be crushed, but not a traditional crushing. So they have to be crushed by hand with hammer, lots of paper and plastic to avoid the direct contact between the hammer and the sample. Then they have to be milled in agate bowls. And for now, I already shipped the samples from Rouyn-Noranda, from the Pontiac, to Germany. They just arrived today, actually. And I'm going to ship the ones from Geraldton today or tomorrow. So, and there's only Thunder Bay missing now. So the next step is in January, to go to Germany, to KIT, where I'll be collaborating with Clifford Patton and Jochen Kohl, and I'll be performing ultra-low detection limit analysis by LAICP-MS in pressed powder pellets. And besides gold in trace elements, as Bitcoin did in his recent paper, we are also going to acquire information for base metals. Thanks.